Okay, let me share the screen here. So I was talking about the other quality tools that we didn't finish to talk about last time, and so one of those is the run chart, and I was just pointing out the run chart is that when you plot against time, performance, output, errors, whatever measures of interest to you, and that plot shows whether or not things are getting better or worse depending on what the direction is. Oftentimes, run chart is used to identify problems when it shows that going in the wrong direction. And at the end of quality improvement activities, also run chart can show you whether or not actually things have improved. So it's very simple to do, and I believe everybody should use run chart on their measure of that's important to them on an ongoing basis. Now, just to show you an example, let's say that CDC. I don't know. This is not from CDC, but I made this example that they will track the infection of various type of diseases in the country. And so, if you think about the cold, over time, they look at every month and percent of people that got cold or other diseases. So I've kind of created 2 years of data here. January going to December, and then again the second year going to December. And if you put them in one column and then plot them as a run chart, you will see something like this. And so you could see that the data really is not as expressive as the chart is, and by looking at it you could easily see that certainly there is a trend and there's a cyclic approach or inherent into this data or disease that we're tracking. So during the winter time it seems to increase, during summer it decreases, so you've got this cycle going on, but then suddenly in the second year you could see things are going up, and this is how the flag goes up. If this was a CDC type of data, they would say, oh gee, something is going on where we're getting significant amount of percentage of people getting sick. And so by looking at the data, then they can decide, whether it's an alarming factor or not. And in a run chart, you could have a target value. Could be that based on the previous data or history, they would know that always there's going to be a few percentage of people that are going to get flu during the year. But then if you calculate the average, and because of this high trend that we're seeing here, the average could be significantly more than the target value, and that's the way the alarm comes. But also there's a cautious in terms of when you're looking at this to misinterpret the data. If you're only looking at a small portion of this, for example, if I was only looking at this segment, well, you can see that things are going down, and you say, well, okay, things are getting better. Or if you're looking at only this segment, you can see things are getting better, but it is really not getting better or worse. This was just the way the cycle works. So you have to be careful in terms of interpreting the data. Particularly, it's important to have a longer set of data in order to see whether or not there is actually a trend in that. Another example here, let's say I was interested in my commuting time, and I'd like to get to work, and I know many of you do commute in 30 minutes, so I started to track the data for 3 weeks. When I leave on Monday, look at my watch. When I get to the office, look at my watch, and then recorded how long it took me. I put it in a column, and then I draw a run chart. Now, looking at the run chart, immediately you could see that, well, there's a couple of things. Mondays, it takes me significantly more time to get to the office because everybody is probably on the road. Wednesday and Tuesday and Thursdays are better, but overall, I'm not making my target. The average of this, if I draw it, is somewhere around here. And so by looking at the data, I have to decide whether I need to leave home earlier or take a different route. That's the value of looking at the run chart and the data in that format. Now, there's an interesting example I found in the use of the run chart. That in this particular example, this is a company that was producing cylinders, and the cylinders in the car, if you see or you know about it, there is a lining inside that that lining gets bored very precisely to tolerance. So if it is kind of a bored larger hole, then obviously it's not going to hold pressure when the piston goes in, and so they have to scrap it. And if it's too tight, they have to, I guess, remill it. But in this particular example, the manager noticed that there was so much or a lot of scrap in terms of the having those bored to be larger than expected. So he talked to the supervisor and said, what's going on? Why do we have so much scrap? And the supervisor gave a very nice explanation, saying that this job is complicated, and the people that we put on the machine, by the time they learn how to use it effectively, they move to another job and have a high turnaround on this. And so the new person needs to get started from the beginning, and so there's a training problem. So the manager decided to check it on for himself or herself. And so he went to the quality department and said, give me the data on a scrap for the past few months, and took the data and plotted them by the operator. And so here to show the timeline is at the bottom, and the amount of scrap that the operator generated every day that was working on. And well, here's an operator that started with a low amount of scrap, but then increased toward the end. And then the second operator actually started at a high level of scrap, which is what the supervisor was talking about. And then as learned how to do it, it dropped lower. While the third one, again, it started low and high. And so you look at this data and say, well, that doesn't sound like the operator learning how to do this well on the job. Now here's operator E. It started with low, went up, then went low. And so that doesn't seem to explain the problem. So he took on himself to plot the data differently. So this time, he plotted data by the supplier of the material. So they were using two different suppliers, X and Y. And so when the operators were using those inner tubes from supplier Y, here it shows that that's the material was used, and then there's material used from supplier X, supplier Y, supplier X. And you look at this chart and you can say, just jump at you that, well, the problem wasn't the operator, as usually people will claim, but it was the material and the supplier. So supplier Y seems to be having the right material in terms of the boarding process, and so you get a little bit amount of a scrap, while the supplier X material wasn't doing as well. And so by looking at the data, then you can decide to kind of only buy from supplier Y and not buy from supplier X. So the run chart, by plotting the data, you could probably kind of make assessment in terms of improvement to the process without too much complexity. This is just a simple data over time. Any question? Okay. So the scatter plot, and we already had that as part of the last week, it's to find the relationship between two different variables. So variable B and variable A, and we want to know whether or not there is a relationship. This is not a causal relationship, but it is a correlation. So what you do is that you've got an independent variable and a dependent variable, and you try to plot them on an XY axis to see if you can notice any trend. So here's an example of a positive trend, project cost versus hours worked. So you know the more hours you put on a project, the higher the cost is going to go. So that's a positive correlation going this way. This is a negative correlation when the task duration or the project duration as a function of how many hours you work per day. This is where the project managers tend to associate or allocate overtime in order to bring the project duration time down probably to what the plan was. So it's a negative correlation here. And obviously there are some situations where there is no relationship. Here the number of employees and employee morale does not necessarily mean that they're correlated in any way. So that's the correlation. Now, why do we want the correlation? Because we find the correlation, you can identify the functional relationship between the dependent variable and the independent variable. Here's the dependent variable will be Y, and the independent variable will be X. And as a result, I have defined, if I get the functional relationship, then I can calculate or predict the value of Y based on the value of X. We know there's always some error associated because not all the points are on the line and there's an intercept. So that's what we did as a class exercise. Now, just to give you a little more insight of what does that, because many of you did pull out the equation and put the R squared, which is a measure of how good it is this functional relationship, or how good is this trend line that we put in for this set of data. So here, let's say that these blue data points are the data points, and you put a trend line through it. Now, the goodness of fit, or R squared, is 1 minus this SS, which is sum of the squares of the residual versus sum of the squares of total. What this really means is that we're taking on the numerator the square of the distance between each data point and the line. Okay, so how far is this, and then you square it, add it to the how far is this, you square it, how far is this, you square it from the trend line, and then divided by the square of data point from the average line. And so here's the average line on the horizontal. And so if you look at this relationship, if the blue SS on the top is 0, it means that every data point is right on the line, right? That's why you don't get any square. So if every data point is on the line, then you get an R squared equal to 1, because this term goes to 0. And that's a perfect fit. If, on the other hand, is this SS blue, then some of this square is the same as the bottom, you get this ratio to be 1, and so the R squared becomes 0. That's where the trend line is horizontal, which means that there is no relationship between the two. So that would be 0. So normally when you look at an R squared around 6, 7, or 8, or 9, that's a pretty good fit. But an R squared of 0.2, 0.3, 0.4 is really not that good. It just shows that there's too much of a variation of data point from the trend line. And the steps to doing the regression analysis is that you're going to need to collect your observation on both variables, and then you can put them out in the columns in an Excel sheet. I'm going to show that, and then plot it and get the relationship. Let me just see if I can bring my Excel sheet up here and go through a couple of these. What happened to my Excel sheet? Do you see the Excel sheet? Anybody sees the Excel sheet? No. Okay. Let me just, maybe it's not shared. Okay. Do you see the Excel sheet now? Okay, so I at the bottom of this, you can see that I have pages for a lot of different things. So I'm going to start with a setup that's that you have a set of data here, and I explained the run chart. So if I was trying to get the run chart for that set of data, this is my observations. You calculate the mean value. Okay, so you can get the mean and the mean of the data, and also the standard deviation if you want. Once you have the mean, the thing is that you put the mean in a column. Just repeat it in the column as you have. And if you have a target, you could also create a column for the target. Now, if I have those, then I can essentially take the 3 columns and go to insert and say I'm going to have this line chart. Okay, and so you get the plot. Now, this is, if you're making a presentation, okay, if you're making the presentation, some of this thing needs to be cleaned up a little bit. So I'm just going to, I don't need all those dots on the, this is just jumping up and down. So let me see if I can, you do a right click on that line, on any of the data points, and you can see at the bottom it says format the data series. And I'm going to just take out the option for the markers, say I don't want any markers, and I close it, and now you get a clean line. You can do the same thing with that axis. You can change the colors, and also you can go up in here and pick up a different, title if you want titles for it. Okay, so you click on that to give you a place. You can just type in your title on the top, on the side, and just clean it. If you're making presentation, then you just cut and paste it to a chart. Do you also see it's jumping up and down when you guys looking at it? I have a hard time keeping this picture fixed. So that was the run chart. I also, let's see what I did the. I'm gonna do the Prater chart. For the Prater chart, that was also both as an exercise, I think, and was part of the exercise. I don't think it was on the exam, but anyway, to do a Prater chart, you're going to need to identify the type of issues. Prater is a principle for prioritization. This economist, the Prater, Italian economist, came with the idea of 80-20, which meant the 80% of the wealth belongs to 20% of the people. Or if you think about your 80% of your revenue come from 20% of your customers. And so, or if your system crashes down and you collect the data, you find out that 80 times is a particular type of problem. So if I have these problem categories A, B, C, D, and F, and I collected the data, and 20 times, 24 times was A problem, 12 was type B problem, and so forth, you need to put them in an order. And if your data is not in order, you can always go to the data at the top here, and sort it out by from going from highest to lowest, and then also calculate the cumulative percentage. To get the cumulative percentage, this item is equal to 24 divided by 65 times 100, and so you get the cumulative percentage. So now I can do set up the highlight the data set, and then go to the again insert, and I'm going to take the column chart, and I'm going to get this. Now in the we want the cumulative percentage to be on a different axis. To get that, you go and put your right click on this one of those data points and see if I can get this thing done. And then you can say select the change the series chart type. Okay. You open it up and say, well, for this side I want now a line chart, and we're going to do an OK. So now I got a run chart, but the axis on this still is on the left side. So I'm going to do it one more time. I'm going to put the right click on that, and then say format the data. No, not the right. It doesn't let me to click it on. The picture jumps too much. So if I do a format the data series, okay, here shows up a secondary axis. You click on the secondary axis and say OK, and here you get the secondary axis on the right is a percentage, and so you get the chart nicely done. The left side is the scale for the frequency, the right hand side. And why do we do the cumulative? Because you could quickly look at the first 2 or 3 items and say, it corresponds to 68% or 70% of the data. Okay, so let me go back now to my other chart. Oh, I was going to show the regression. So let me go back to the. Did I have the regression? I may not have the regression. The regression it's similar to just how I wanted. You put the 2 columns of your data X and Y, then you highlight it, and you go up to the type of plot to insert and pick up the scatter plot. And most of you did that. You get the scatter plot. Then what you have to do in order to get the equation, you need to right click on one of the data points. When you right click, it opens up a window. which you could select whether you want a linear relationship, you want an exponential relationship. It actually opens up on the linear relationship. So you have the relation, and at the bottom of that you also have the choice of picking up the equation and the R square, and you click on those and then say OK, and you get your chart. Again, when you get your chart, you probably need to go back up on the top and pick up the titles and make it nice. If you're making a presentation, you want the chart to look nicely, and you can even also change the scales and so forth. But once you have the equation, then like in the exam that we had, estimating number of days for programming 225,000 250,000 lines of code, then you put the number of 1,000 lines of code. Some people made the mistake of putting 250,000 in here, and so you got thousands of days, which was pretty high. But the whole dimension was in thousands, so you put 250 here for that equation, and you get the number of days, which was about 79 or 80 days. So that's how you do the regression. And I already went through the Pareto chart, and it shows how you do that. I did the calculation. It's a different example of Pareto chart of let's say that you were in banks, or people filing application for credit, and somebody reviews those application, and if there's a problem with it, it would delay the process. So in this particular example, there was one that didn't have an address typed on it, or didn't have a signature, or missing some other data. And so if you collect that over a sample of these applications, you can then sort them out by the type of problems that you have, and then plot them as a Pareto to say where is the most of the problem the customers have. In this particular case, the biggest problem was not having a sign or signature on the application. The second was not having an address for sending back, and some other missing data. The point is that once you have this, you can kind of show that this is probably the thing that we need to work on with our customers, or with our employee, whoever is handling these issues too. And if you can knock out this one column, that significantly reduces the number of problems in the application. So that's the Pareto, and the Pareto always starts from the left side with the highest column, so it has to be sorted out, as I showed in the other example. And we also showed the cumulative percentage, and I show how you get that out of the Excel. Another tool that's very important in quality improvement is the cause and effect diagram. It's also referred to. I will post this on the after we finish with the recorded. Cause and effect diagram. It's also called a fishbone diagram, coming from the Japanese who invented it. And the idea here is that you have an effect that you want to find its cause. If you find the root cause of a problem, then we can eliminate it, and that essentially to get rid of the problem in the future. So you put the effect on the head of the fish, and then you got these major bones, and then the type of category generally could be like people issues, it could be material issues, it could be equipment issues, it could be method issues or procedures. And then we start asking the question of, what was the problem with people causing this, and so forth. So, but the cause and effect diagram, it's a team process. Now, it's not something that you just come out with an answer. You sit down in your office and come out with an answer. The most, I guess, prominent use of this is that you have a team. You get in a conference room. You put a flip chart on the board, or you could use the computer and put in the screen on, and essentially create the skeleton and say, okay, here's our problem. And the main categories could be methods, machine, material, people, as I said, could be places, procedures, people, policies, hardware, software, whatever you think are the categories of the causes for that problem. And then you brainstorm and say, okay, why this could be, and people with ideas, particularly those who are familiar with the process, they can come out with the potential causes for the problem, potential root causes. When you start asking this question, why this is a root cause and why is this a root cause, and you're adding more and more detail, but at the end you can sit back and look at it and say, okay, among all of these potential problems, which one do you think is the most likely problem, and then the team can decide on using some team approaches to come up with the voting and or other ways of finding out, giving picking the most likely causes, and then you can go and address that and look at it, see whether or not that fixed the problem. So here's an example I picked, is that the effect will be a poor gas mileage of the car, and this is an older example used in teaching. So most cars today don't have carburetors, but it shows that the carburetor is a problem, or potentially could be a problem. So we've got a poor gas mileage, and it could be the machine itself, it could be the method of driving it, it could be the people themselves, it could be the material. And so you start with that, and then you start asking the question, well, what could be the cause in here? Well, I mean, understanding or underinflated tire could be the cause of poor gas mileage. Or the carburetor adjustment, this is all the cars, so that could be a problem for gas mileage. Well, what about the methods? Well, driving too fast, that uses too much gas, or poor maintenance could be the cause of it. So people start pointing out the type of potential causes. You put them in, then you're asking furthermore question on each of them. Why the poor maintenance could be the cause of this, and you could see, well, because we didn't do maintenance, or we don't do maintenance as often, routine maintenance, because it's too costly, or because the driver doesn't have too much attention to that. So anyway, at the end of this exercise, they decided that the poor maintenance was the root causes. Now, in a different example, just from my own experience, when I was at Bell Labs, there was this issue of why can we get the projects out of the Bell Labs into the development fast. And so they asked me to do a root cause analysis of this and figure out what was the problem. So what I did is essentially created with my team, we created a fishbone diagram like this. Then I went out to various business units and talked to the executives and engineer and asked them what they think is the cause of the problem. And each time when I heard a particular thing, I just marked it as one time I heard it, and then I heard it again second time, or I heard it from another person. So I started to add numbers on those items that I had, and if something else was presented, I added to the list. And so at the end, I had these issues listed here, where most people, if there was one item that a lot of people said that, I kind of took that as part of the top of my list. And so when I reported back to the vice president, I kind of summarized that as, here's the thing that most of the people in the business unit think is the cause of it. And so that was one way of finding out the most likely root cause. And here, the team sitting in the conference room, they decided that poor maintenance was. So there could be a number of different ways at the end. The whole thing is that the whole process is a brainstorming process of identifying what potentially could be a root cause. Once you have all those potential root causes, then you have to look at it and say, okay, among all of these, which one are the top one or two that we think is the cause? Then you have to apply that or do something about it to see whether or not that actually was the case. So that's how the root cause analysis works. There is no magic, it's just the process. Okay, any questions? I think this was the last chart from the first module that I had. So I'm going to stop here if there is any questions to answer before I go to the SPC module. So anybody? And you guys hearing me well? Because even though I can't hear you, it's very important that you hear what I'm saying, because that's the and you can type on the corner here, and I'll be happy to respond to questions. Okay, if there is no, I'm going to close this module. And let me open up the other module. So this is what I call it, statistical analysis part 2. We're really focused on chapter 11, 12, and 13. This is what we're doing this week, next week, and chapter 13 dealing with the question of Six Sigma. So as part of the outline, I talk about the basic statistic covered in the first module and the quality tools. You cover the normal distribution And the use of the table also, last module, it's all, if you didn't see it, it's already recorded, available to you. And so tonight I'm just going to focus on this. If I finish all of it, then we're done. If we didn't finish all of it, my plan was to only hold about an hour or so. Then we could probably follow up on the Six Sigma next week. But let me see how far we can go with this. Okay, so I'm glad that no, I did not interview everybody in the company. You know, the way the AT&T was set up is that the Bell Labs essentially developed ideas in the labs, and then whether it was related to transmission or it was related to switching or whatever the product was, it went to the development unit and they essentially made it into a product. Now, I was taking it too long from the VP perspective, from the ideas getting from the lab into the development. They wanted that, I mean, everybody's interested in shorter time, right, and shorter cycle time. And so I interviewed a cross-section of people, both engineers in the development as well as the lab, as well as the managers and the executives, and I put all of that together. And so at the end, I look at what was the particular issue that most people said that was one of the causes, and I kind of reported that back. I was just pointing out that it's not always just in the conference room sitting back and saying, okay, let's pick up an item. There are other ways that you can get from the people that have knowledge of the process. This is where the key is that when you're doing a root cause analysis this way, you're going to need to depend on the people that have the knowledge of the process and the consensus among them. So if more people say it is the poor maintenance, then that seems to be the likely cause of that poor gas mileage. And so then the next thing is to actually go on and implement some changes, maybe, and as a result to see whether things are improved. And so that's what I was showing, a different way of reaching some consensus. Because you look at that fishbone diagram, and there are, there could be, in fact, in real example, you could have hundreds of items listed in there. Well, it's very difficult to say, okay, which one is it? So we're going to need to have some process of elimination or prioritization to come out with the way we think is the root cause of it. Okay, so let's start with the control chart. That's what we are studying this week. Now, control chart, I just showed a few minutes ago a run chart. Now, control chart is nothing more than a run chart, but it has control limits. So if you look at this picture that I have in here, and I hope, do you guys see the PowerPoint? Anybody see the PowerPoint? Okay. So this is very similar to the chart that I had. In other words, you're having some measures of the output that's listed on a timeline. But if I have control limits for it, then I have a control chart. If I don't have control limits, then I just have a run chart. Now, the control limits, when Schuhart created the control chart, he looked at 3 standard deviations. So if this process was normal process, and you get the output, the expectation is that every process has some variation in there. There's an inherent variation in any process. If that variation is randomly distributed around the mean and is within that 3 standard deviation up and down, then we say that process is in control. So in this case, these data points are between the lower limit and upper limit, but I've got this point in here that's outside the upper limit. And so in this case, we said this is out of control. When it is out of the control limit, it is out of control, whether it is up or whether it is down. Now, in the exercise that you're doing this week, beside a process being out of control, the process could also be, we call it unstable or erratic. The idea that is that these variation of the data points are not randomly around the mean, but it looks like they are somehow organized in some way, that are affected by something. So in this case, you could say, well, I've got 4 data points that are below the mean, and so that's something I should check. So the process still could be in control because it's not outside the control limit, but it could have some other issues associated with it. So when you look at that exercise, you may want to make that distinction between whether the process is out of control, or the process is unstable, or the process is erratic, or showing some other view that means that it is not randomly distributed. Something is causing it to be all on the bottom or all on the top, or too many of them in one area or the other. So now, just to show you, if you look at this picture and project every point to the y-axis, okay, if you kind of, let's say if I had an accordion and I pushed all of these points to the y-axis, I get a histogram, because all those points that are in the same area, we're just going to stack up on each other, and so I'm going to get a distribution. That's what it is. I cannot write on this one. But it shows that there is a distribution that goes around this with the mean, and if it is normal, it's going to be right on the mean line. And so the 3 standard deviation up and down is really covering the 99.7% of the distribution. Now we're plotting it this way because we are plotting the data points on time, and we're putting the control limit to see whether or not any point is out of control. So here's an example. I've got a process here with the whatever the process might be. You can see that these data points are going up and down around the mean, and then, well, just there's a point, an observation that's outside the control limit. We're saying that this process at this point is out of control. Now you go and find out, it could be some causes that has resulted this. Let's say if this was the